Sorry to startle you like that. My name is Alan Shade. I'm the Dean of the Maroon Saman Faculty of Engineering and Architecture. We have with us today Dr. David Morig. His research focuses on the physics of how terrestrial, submarine, and planetary landscapes evolve. They study the behavior, his group studies the behavior of topography generated at the interface between a granular material and a moving fluid from very short to very long time and space scales, with particular emphasis on processes controlling channel formation both on land and in the deep ocean. David got his undergraduate degree in geology at Pomona College in Claremont, California. He did a master's and PhD at the University of Washington in geological sciences. He's presently the Associate Dean for Research at the Jackson School of Geoscience at the University of Texas at Austin, Hook'em Horns. Are there any other Longhorns in the room, just out of curiosity? Yeah. Great, 2, 3. Okay. Yeah. Well, we're wearing our honorary pins today.
To keep their hands up.
Okay. Someone just keep their hands up. Well, we have a fresh graduate, Elsa Madhu, back there. He's also the John Brick Elliott Centennial Professor in Geological Sciences in the Department of Geological Sciences at the Jackson School. He was formerly Associate Professor of Geology at the Department of Earth and Atmospheric Sciences at MIT, EAPS. And before then, he was a postdoc at the University of Minnesota and also a senior research geologist at Exxon. He has more than 100 publications, some of which have garnered awards, and he has mentored more than a dozen doctoral students. David has also won numerous teaching and faculty performance awards. I was quite impressed with that. As a dean now, I'm impressed with these things, as much as I am the research, of course. Today he will be talking to us about a research initiative at Texas addressing Earth in 2100, water, energy, land use, and climate. This subject is near and dear to me personally, but also to the Maroon Saman Faculty of Engineering and Architecture as a whole, which recently made human well-being its central driving concern in its pedagogy and its research. We are embarking on an aggressive 5-year plan to align what we do, teach, and learn with what is needed to address the wicked problems that we find ourselves increasingly unable to ignore. These problems require intellectual agility, radical collaboration, and tolerance for ambiguity. I look forward to hearing about how Texas is cultivating this mental landscape. Please join me in welcoming David to AUB.
Well, thank you very much for that introduction. And thanks to everyone who has made this trip possible. It's been a wonderful first day. And I'm looking forward to an equally wonderful next couple days. So thank you very much. So what I'm going to be doing today, I'm trying to decide where the right place to stand is. I'm not sure. Maybe I will try behind here. I feel like I don't want to block the screen. But is that going to work? Am I blocking people's screen? Okay, then this is where I will stand. So what I'm going to be describing a large initiative that has begun within the Jackson School of Geosciences, and it has become recently even a larger initiative with the announcement that the very first grand challenge project of the whole University of Texas at Austin is essentially adopted from this. Our initiative is called Earth 2100, water, energy, land use, and climate. The university-wide initiative is called Planet Texas 2050, but when you read what they're trying to do, it is very much inspired by, in fact, 2 of the leaders are members of our faculty. And so I'm going to do some science and talk about some things that I'm very excited that my colleagues are doing and show you a little bit of what I'm doing, and then talk about how we take that science and use it for societal purposes. I can't give you the answers, I'm afraid, because I don't know the answers. I give them to you if I knew them, but I can show you what we're trying to do and what kind of information we think we need to do this better. Now, Texas is really a land of extremes. It is a place where we have extreme drought, and here is an example of one of our reservoirs under duress just a couple years ago. And we also have extreme precipitation events. And so we have to learn how to work within that feast and famine to build the societal infrastructure to thrive in a community that they're predicting will double its population in the next 50 years. So we're already 28 million people in the state of Texas, and the projection is that it could go as high as 50 million in the next 50 years. And so how do we deal with that? And part of dealing with that successfully is actually understanding the environment. And the environment is definitely a challenge that the geosciences have a lot to contribute to. They can contribute to that through direct observation, through experiments both in the field and in the laboratory, from analysis of pre-existing data and remotely sensed data, and through numerical modeling. There are a series of questions here about motivating why we're doing this and why it's important. I'll leave you to read those questions if you want. It's very clear to me that the people in this room understand that these things are important. So I won't dwell on those. What I will give you a sense of is the roadmap of where I hope to be going. I'm going to go through these different points, probably talking the least about numerical modeling, because I'm going to make the point that at this moment in time, we probably have more advanced numerical models when it comes to looking at the coupled systems that represent the environment than we actually do in these other parts. We need to be able to test our models and to benchmark our models, not necessarily make them look better. So that I'm going to be talking a lot about how do we get the kinds of data we need to really make sure that our models are accurately describing our environment. You're going to be seeing work from many of my colleagues. We probably have a couple dozen faculty who specifically work on integrated environmental science. You can see that there's a list of 8 of them. There should be 10 people that I'll be showing their work today. I'll call that out when we actually talk about that, their contributions. So this is I study landscapes, and one of the things my group spends a lot of time looking at is coasts and coastline change. We have a very large project looking at the Mississippi River Delta, where there's an extreme amount of land loss going on. We want to be able to use nature-based engineering to minimize the rate at which that land is actually being lost. This is our test delta. This is a subdelta of the Mississippi River that there's so many ways to navigate on the Mississippi that this one's been left alone in a relatively natural state. And so we can instrument this in such a way to understand how the ecology, the hydrology, and the biogeochemistry all interact with each other to build land. And there's a model here showing just a tracer from one of our many kinds of models. We build many kinds of numerical models. For those who think about the Earth's surface over long time scales or over large spatial scales, you know that there is no one right model. There are many models that are better or worse depending on the questions that you're asking. So this is a fairly simple model, but it has the advantage of running very fast. You can see the tracer's gone down a couple times now. The question is, it looks right, but we have to get, it kind of looks right. Our intuition tells me that looks right. But I'm going to argue we need to get well beyond what I call the eyeball test. We need to be able to say quantitative things about the exchange between land and the channels and the implications of that change and exchange. And in this case, the implications are huge because this is a site that sequesters a lot of carbon, and also it is a nutrient factory in terms of sequestering that as well. So understanding what's going on there is very important for this particular environment. So we're going to use models to guide observations, like where to make the measurements, and then we're going to use those measurements to build better models. That's the way that we're trying to move forward. So here's sort of an outline of where I want to go. I'm going to talk about environmental resiliency. I'm going to really focus on water and plants and climate and soils. These seem to be things that should resonate with everyone here. We live in a very water-stressed environment. Well, we go from too much water to not nearly enough water, depending on whether you're in the eastern or the western part of the state of Texas. But I'm going to focus on those areas that end up being stressed and show you the kinds of data we're collecting to do a better job with understanding the water cycle. And then after doing that, I'm going to move on to talking about both Earth in 2100 or Planet Texas 2050 and show you the challenges that we have with connecting water with energy with society. I mean, we have to do this successfully. So I'll show you how we're thinking about approaching those things, the kind of data we need, and then where we hope to go into the future. So, what I'm not going to talk about much today is surface water. And even though that's mostly what I do, this is a remarkable achievement. David Mayment in our civil engineering department and Liang Yang in our geology department, among others, have played an outsized role in producing the national water model, which predicts the instantaneous surface flow in what is this crazy number? 2,670,000 river reaches simultaneously. So they route water and floods down the whole network. This is an amazing achievement, but when you get to the point of being able to do this sort of thing pretty well, it means that the science is relatively mature. So this is not where we're going to put our effort today. What I want to talk about is plants. I have a new colleague, Ashley Matheny, whose office is right next to mine. She's an eco-hydrologist, and so I get to see her enthusiasm every day, and I'm going to show you the plumbing of plants and why that is important. And then we'll move on from the plants to the soil and the new measurement tools that are being made to understand what the groundwater is in Texas and other places. And then finally, the control of the soils on both drought and on flooding. So, a lot of you in this room probably know this, but I want to make this point again. Transpiration, the release of moisture from plants, is really the mechanism that drives the terrestrial water cycle. And I'm going to hit that home in a couple ways, but I'll start that right down here. So this is for the Amazon basin, the godfather of hydraulic systems. And if you look at these numbers, they're staggering. Trees release 20 billion metric tons of water each day. The river itself pours 17 billion tons of water into the Atlantic. But these are sub-equal to each other. You cannot understand this system, the weather and the climate, without understanding what the water is doing in the plants. And that is something that we have far from a complete knowledge of. Another just example of this is unfortunately in Kenya, where there's a real-time disaster going on. This was an area that had rained historically every day. It has been clear-cut, 264,000 plus acres have been deforested since the mid-1970s for farmland. The idea was it rains a lot here, we don't need to irrigate, we'll make very good farmland. Well, when they cut down these trees, they totally changed the local climate, to the point where in 2009, which was the worst year of all, they had no rain. So it went from a tropical rainforest to effectively a desert. And it did that by losing the water control of the trees itself. So this is a big issue, and it's an issue that we need to both understand at the level of an individual tree. It's an issue we need to understand at the level of a forest, and then we need to aggregate that to the scale of a continent. And so we're going to start to the tree and to a forest. I'm going to show you some results from that. But the goal really is to ultimately put this into hydraulic models, weather models, and ultimately climate models. And there is a lot here to understand drought mortality. When plants are truly threatened to the point of dying, that is directly tied to forest fires. We have tremendous forest fire hazards in Texas, as does much of the world that is semi-arid to arid. These things are directly connected to each other, And then, of course, there are implications for agriculture. So, how much water does a tree actually move? Did this actually start? So let me start this video. This is, so what you're going to see here is Dr. Matheny has just installed the ports for her sensors. The sensors aren't even in yet. She's just installed them. And watch, this is a real-time video, and hopefully you can see here, it's shaky, and down here, you can see the sap just dripping out of the birch tree. The point here is that these trees have a remarkable amount of fluid in them, and that amount of fluid changes with the day. It stores it during the night, it releases it during the day, and we want to be able to understand those things because they are the largest component of the terrestrial water cycle. It is dynamically regulated. They are responding to their environment and probably to adjacent trees, which makes that quite interesting. Different trees do very different things in the case of stress, and I'm going to show you one example of that. And because different trees do very different things, upscaling this is a challenge that that's really being worked on right now. So, how do you study the plumbing of trees? Well, if you don't know, you take in sensors that you've used before for studying soil moisture and soil content and say, maybe I can put those in trees. And lo and behold, that in fact works. And that's what Dr. Matheny has done. These are actually originally soil samplers that have been installed in the various trees. There's Dr. Matheny, 5.5 meters up in the air for scale. So she will install these up and down the trees to understand where the water is and what the water is actually doing. What I want to show you now is to give you a sense of the challenge we have with upscaling this to the climate cycle. So there are 3 lines on here. If people are colorblind, I apologize already. So the black line, which is this bottommost line here, this is the actual water content in meters per meter cubed. So this is the amount of water per volume of soil in the system. And what you can see here, there was a rain event right here, but overall, this is drying out. So we're going into a pretty extended period of drought. Extended period of drought meaning 25 days of not rain in a very sandy soil. So it dries out very quickly. And we have 2 species of trees here. The blue line, which stays high here, is an oak tree. The line that starts out high and then drops precipitously is a maple tree. And what was surprising to all of us was not the fact that it goes up and down. All of these points where the water storage is high, that's sort of in the morning. Stomatas are closed. It's collecting water. Then the release happens during the day, collecting, release, collecting, release. That makes sense. What was terribly surprising was the very different response to this sort of month-long drought. The maples and the oaks start out almost under unstressed conditions, basically one and the same. But as the water moisture, the soil moisture decreased, the maple became very, very stressed. In fact, down to the point that it wasn't really even able to store and release any water anymore. These trees were actually well on their way to being stressed to the point of dying. Whereas the oak essentially was unaware that this drought was happening. So this, in fact, has a lot to do with the root structure of these trees, and I'm going to talk more about root structure and deep groundwater in just a bit. I mean, just looking out as we were flying into Beirut, I saw a lot of rocks. Of course, I'm a geologist. I love seeing rocks, but it looks like a lot of the soil is fairly thin, and so water in fractured bedrock must be a big part of your story here, and it's something that we're working on a lot at the University of Texas because we're finding that actually it adds the resiliency of the forest much more than we anticipated. There's a lot more water being tapped by very deep tree roots than we had really ever imagined before. But here is a very different response to a drought, and now our challenge is to understand how to how to upscale this. We don't have the answer yet, but the goal is to go through species by species, understand those things, and then to try to make models that make sense. Now so I showed you that remarkable video of before the sensor was put in, of the sap just pouring out of the tree. What I'm going to show you now is using these sensors to do something very different, but in many ways equally important, and that is to predict wildfire ignition. So I think overall, we have a tendency as humans to suppress forest fires, which means that everything being equal, there's a lot more fuel for fires in existence today than there has been in the last couple hundred years at least. And that can lead to tremendous fires, of which I am very aware. This is where Belle and I live. This is Austin, Texas. This is the Bastrop fire. It lasted for 5 weeks before they were able to put it out. You can see the final cost here was over $300 million US dollars. 1,600 homes were lost. The air quality was bad. I mean, this was a tremendous event. Question is, should we have been able to predict this more than just saying it's been dry for a while? 2011 was a drought year. We're going to talk about 2011 again in just a minute. We knew that there was this likelihood, but what we are looking to do now is to take those same tree sensors and install them in forests, in stressed forests, and in dead wood to get a sense of the moisture content such that we can develop a way to say when we get below certain water contents, the combustibility of the fuel goes up. And so we can be on high alert as a community at times when that happens. So we're going to instrument areas to lead for better prediction of the forest fires, because we're constantly being asked to do more with less direct observations. And so the goal is to put these out there and just have real-time connection to these areas. So we can use them to predict forest fires, which is certainly something we're going to be doing. This same drought killed a lot of trees. It didn't just combust fuel that was already there. The drought was, so this is in 2011. You're going to see a plot later on in my talk. At that point in time, by the end of the summer, 95% of the state of Texas was in extreme drought stage. It was scary what was going to happen. Of course, then we had far too much rain, which I'll show you, and that led to a different problem. The question is, how do we understand and predict when this is about to happen? And to do that, we really need to be looking at the soils. And so one of the things that we're studying in great detail is the groundwater system. And far from just the traditional aquifers that we as people get our water from, but things like the moisture content of the soil and of the bedrock, which have historically not been as well studied. It's easy to understand why to do this. Soil moisture has an outsized control on temperature and evaporation, and so as a result, it has a huge effect on both our weather and on our climate. It can both affect stream discharge in a negative way. If the soils are very dry, even with heavy rains, the rivers, the channels don't flow. If the soils are saturated, you can get a significant flood from a storm that otherwise wouldn't really amount to anything. So this is Lake Travis in 2013. During still the extended flood period, you can see these houses you used to walk up onto the right there. That tree line is where the historic reservoir level actually is. So a tremendous drop in water. This is the water source for the city of Austin. So there was a lot of concern about this. And so this is in the fall. Then just a little bit later, we had tremendous flooding. So this is in downtown. This is Stevie Ray Vaughan, one of our local rock and roll heroes. We have a statue for him right in the downtown city. And this is Stevie Ray Vaughan. I should have moved this up so that the hats were at the same scale. But you can see Stevie is now, there's about 10 meters of water flowing through downtown. And this is in a place where we have 5 dams that are supposed to regulate flow, but yet we were still unable to do that. So let's talk about what we're doing with understanding soil moisture, but first, just to make sure everyone's on the same page, I'll be talking about water content or soil water content of soils. That's just comparing the volume of water in the soil to the volume of soil. So it's just how much of the space in between the grains of the soil are actually filled with water. We'll talk a little bit about gravimetric water content, so that's comparing the weight of the water to the weight of the soil. This ends up being very important because gravimeters are a way to assess the regional storage of groundwater that hold a huge upside, and we're working to take advantage of that tool more. And then also just soil water storage, which is just looking at the depth of the water column compared to the depth of the soil. So they're all giving you a sense of just how much of the space between the soil grains are filled with water. So we can measure the soil, and we do. We measure the soil moisture in all kinds of ways. They all have advantages and disadvantages. There's still nothing better than digging a hole and looking. But it takes a lot of time. Now we can use fancy neutron probes and NMR, various things to get really direct measurements of the water content. But this is very labor intensive and therefore very expensive. And it's always at a few points. So it's far from synoptic. Now we can put in sensors, so we can dig our holes and then put in sensors to get long time series. And that is certainly a step up. But we still have just dozens or hundreds of points over thousands of square kilometers. So there's still an issue there. We have numerical models. We take advantage of conservation of water mass, and so that has to balance, but it's hard to parameterize the globe or even the state of Texas to really understand what's going on there, and they're even harder to validate. Again, a lot of these models look about right. The question is, how accurate are they? And are they accurate for the right reason? And we also use satellites. And satellites clearly hold a lot of allure because we can get pictures of whole continents, if not the whole globe. But we have issues of resolution, particularly spatial. Even we're going to look at the SMAP satellite that was launched in 2015. It is the best thing that at least NASA has going to look at soil moisture, but a pixel is still 9 by 9 kilometers on a side. That is a big area. And perhaps more importantly, satellites give you a view of the water content in the upper soil that's about like this. And each of you in the room can decide if that's a very good description of the whole water column. It's a reasonable proxy, but it certainly is limited by its depth. So here is the SMAP satellite. It uses both radar and a radiometer and the L-band sensors and the radar to actually get a sense of what the moisture is and how either frozen or liquid the water actually is. It produces perfect maps like this. The gray up here is where we actually have frozen landscape. Here's the water content throughout the North America. Texas is right in here. It goes from pretty wet to pretty dry, which is what it's characterized by. So the question is, how do we test this? And one of the things that we're actually investing in at the University of Texas is a soil network. We're doing this with other universities in Texas and with the state of Texas itself to put together the Texas Soil Observation Network, which we call TEXON. And one of the main things that we've been doing recently, my colleague Todd Caldwell has been working in an area in central Texas here, trying to put together a perfect pixel to test the SMAP satellite with. What can you build a perfect test, even if it's just 1 pixel in size, a 9 by 9 kilometer area, to really understand what the water content is and compare that to what the answer we're getting from space. So we have over 40 stations. This is going to keep growing with time. That number is probably in fact, I know it is already out of date. We're collecting soil moisture at still pretty shallow depths, up to half a meter. Of course, we have real-time data collection, validation with gravimetry, which basically weighs, estimates the mass of the water in the soil. And perhaps just as importantly, all of this data is available on the web for anyone who wants it. And I do think that if we're going to do science that's for the benefit of the society, we have to actually get that information out there for everyone who wants to use it as soon as it's available. So you can go to the Bureau of Economic Geology's website and download this data and look at it to see what they have going on. So I've already talked about, can we build the perfect calibration validation pixel site for the SMAP satellite, and then can we just improve data products by having more real-time data? How do we use this information to better predict both oncoming floods and oncoming drought conditions? And then it really helps with management of all of the natural resources. But this is still really shallow. One of my other colleagues has been studying what she refers to as rock moisture. So Daniela Rempe she's going deeper. She's investigating weathered and fractured bedrock. And of course, a lot of the limestone that I think I saw out of the plane window must be very fractured, and you must have, a lot of bedrock water. And the question is, to what degree is your ecology tapping into that deep water? Because it probably is, and that makes for a resiliency of the forest that we didn't necessarily understand before. So we're taking what we know from soil science and as an earth scientist, adapting that well down into the unweathered part of the subsurface. And here's just an example of the sorts of things that she does. So this is using NMR to get at the actual rock water content through time. Notice the scale here. This is now a 20 meter, not a 50 centimeter measurement of water content. By this point, this is right where there's no change here anymore. You're actually at the water table. So the water table is 19 meters below the surface here. The soil is soil and saprolite, so the heavily weathered material is up here at 4 meters and above. You can see there's a lot of seasonal variation like you would expect. This is a Mediterranean climate where this has been taken. And everything between 4 and 19 is the fractured bedrock. And in fact, that accounts for as much or more water than the soil. And it allows for our trees to persist under conditions that otherwise... This is in California, yes, sorry, yes. So Daniela did this work in California at a place they call Rivendell. Her advisor is a great Tolkien fan. But she is now actually doing these same things, instrumenting these same things in Central Texas. And so we're growing this. And the hope is to actually take what we know about fractured bedrock and extend the whole critical zone from the soil all the way down to the groundwater table so that we really know what's going on in these systems. This is the station that we've already built. This is in the Davis Mountains of Texas. Again, this is fractured basalt, and the trees, there's almost no soil here. And so we're looking at a fractured bedrock's history and comparing the residual water level to the gravity measurements to direct observations in the well to get a sense of both at the well scale, at sort of the kilometer square scale, and then up ultimately to the satellite scale. But let me show you something that we can do even using the satellite data. And this is important for flood prediction. In the US, we have our U.S. Geological Survey and the Army Corps of Engineers that is charged with actually monitoring rivers and streams has been under duress in the sense that the funding to do that monitoring has been systematically cut for many years. As a result, we often are now caught unaware when floods start to happen, because we have extreme rainfall and this flooding can start to happen. And this is an example of those, an example of how we can actually use SMAP data to know when we should expect a flood to happen. So Austin is just right off this map. This is the Blanco River. Each of these red dots are places where SMAP is actually collecting data. So you can see there are a dozen or so sites within this drainage basin. And here is the interesting thing that we want to try to use to understand predicting the flash floods better, which I think would be of great relevance here as well. There are a number of things here. This is just the precipitation. It had been very dry, and then in May of 2015, there were a number of storms and then another dry period. And you can see the cumulative water precipitation here. But let's look down here. So we're going to look at the first really big 5 storms of that time. And look at, this is the stage. So this is the water level and how the water level changed through time. The first 3 storms effectively had no additional rain, no additional runoff in the channel because the soil had been dry. Nothing happened. The 4th storm, there was a little bit of a flood, but not much. The 5th storm, by the 5th storm of that month, the soil was totally saturated, and we had a catastrophic flood that we were caught unaware because the gauges in the upstream area of this catchment had been decommissioned. So we didn't know that this flood was coming. And if you look at this, you can see that the water level in the river went up at the first town that it hit 11 meters over about an hour and a half. That is a catastrophic event. And you can see what it did here. There were fatalities, there were lots of homes destroyed, there were trees that were hundreds of years old actually ripped out by their roots. So this was an unusual thing. 4 bridges were actually destroyed, so it affected commerce for a long time to come. And it looks like the SMAP data, if we look at this, is the volume of water content in the soil, and at about 0.2, we weren't getting much of a contribution associated with these floods. But when we exceeded 0.2, we started to get these really large floods. So it looks like there's a tool there to make a prediction that we have to be extra aware of every rain event of the possibility of a flash flood and not be caught off guard like we are. So we're using these and the fact that we have many floods to start to develop warning systems to help society. Now I have one last movie to show. Flash floods, I'm a geomorphologist and a sedimentologist. I look at how landscapes evolve. Flash floods and the transport of sediment by flash floods is not like steady uniform flow. And so we are modeling this in the lab in a 100-meter flume with flash floods that we can release water at meters a second and watch gravel move. And it moves and sorts itself in such a way. So these gravel are about fist size here, in such way that the river moves much more sediment than our standard sediment transport codes would expect, and they stay much more mobile for longer than they would expect. And it's all about sorting and the way that particles interact with each other when you have a transient versus a sustained condition where they can, self-organize. So if you're interested in how sediment moves down your channels, definitely come talk with me. I'd love to talk more about it. But I'm going to end by talking about how do we take this sort of stuff. So these are just pieces, new pieces for us to put into a water model to better understand our water resources in the state of Texas. But what are our challenges for doing that and applying it? So here is Texas. This is information. Michael Young, who's a colleague of mine, he's the assistant director of the Bureau of Economic Geology, is really taking the lead in many aspects of this. So I'm going to give him a call out right now, and many of these slides are his. We have a challenge of stressed conditions more extreme weather, both drought, heat, and floods. How do we support the fact that there's a good chance that our population will double by 2015, which is staggering, at least to me, is staggering. And the goal is to make Texas more resilient. How do we do that? Well, ultimately, we're going to have to take advantage of models. We're going to have, and they're coupled models, we're going to have a land use model. We're going to have an energy model, because with all those people, we need energy of all kinds. I mean, that's just a fact. So we have to put that in there. We have to have a water balance. And then we have to smartly organize these. We have 28 million people now, going on to 50 million people, nearly doubling in not even 50 years. So in order to couple these, I mean, this is a grand challenge in modeling, but you have to have all the pieces of this right to get a model that gives you an accurate result. We can give you a great model that looks pretty, but it could be totally inaccurate. So what are we doing? And Texas is an interesting place to try to do this kind of work, because it is surprisingly isolated from the rest of the U.S. People who grew up in Texas like to imagine that they're still a republic. We were a republic for a very, very brief point in time. But we do have a lot of things that still are pretty Texas-centric. One of them is the groundwater. Nearly all of our recharge and groundwater resources are directly in Texas. They don't interact with either Mexico to the south or Oklahoma and other states to the north and the west. So sort of what we do with our groundwater is either our success or our fault. Most of our rivers, I mean, our biggest rivers actually extend into New Mexico, but the catchments that are actually contributing all the water, other than the Rio Grande, which is another story, and actually at the moment doesn't have much water in it, so because we've drained it. But all the surface water is essentially in Texas as well. So we have an opportunity to affect change because we control it at the state level. So we have the control of the water, but nature does some pretty crazy things. Maybe many of you saw Hurricane Harvey and the effects of Hurricane Harvey. Those of you who were at my talk earlier today saw what happens. My particular field area, this storm dropped 1.1 meters of water in 2 days, rain. When you're in a rain like that, you almost have to cover your mouth to breathe. It is coming, it's undescribable. In fact, it's hard, you look up and you go, how can this all be, what was the moisture content up there? How does this work? But it does, and in a place like Houston, it was to devastating effect. Of course, it brought out the best in people, and we called it the Cajun Armada. Everyone's duck boat and fishing boat got brought out and to rescue people. And it was a good thing that we were doing this individual by individual, because the state and the federal government weren't prepared to do what individuals actually did for their neighbors. That was going on, and then an interesting thing happened in Austin, which got some rain, but not too much. The threat of the refineries being damaged in the Houston area caused a run on all the gas. Everyone suddenly decided they needed to go get gasoline for their cars. And all of our gas stations ran out of gas for 3 days, which you don't think is that big a deal until you live through it. And then suddenly there are a lot of people to whom that's a very big deal. And that was not caused by anything other than panic. And so things are really, really interconnected. So as I already mentioned, we have extreme drought conditions. The drought of 2011, more than $8 billion in damage. It took years for the reservoirs to recover. So we have to feed this into our understanding. And then the most frightening slide I have is this one, which is looking at the population. So this is all percentage change over the next 40 years. You can see negative values are very few in here, and these are actually in counties that mostly just have agriculture to start with. So there aren't any people to start with. All the places that have significant cities are all increasing by 50% or greater. So it's how do we put this into it? And the other thing to realize about Texas, when you look at Texas and you drive across Texas, it looks like it goes on forever, because it does. But Texas is actually the most urban state in the US. More people live in cities, a greater fraction of the people live in cities in Texas than any other state. So we have to get cities right. And so we're interacting with architects and landscape planners every day to try to understand this. Because our resources are stretched. This is, of course, in a unit that I love, acre feet of water. This means nothing to me. It never has meant anything to me. But 1 acre foot is basically 1,200 cubic meters. And this is just how much water we don't have in our water system today. And it's just getting worse and worse and worse. And when you take these numbers and multiply them by 1,000, these numbers are large. They're so large I don't quite know what to do with them. But we do have this huge supply challenge. So we need to regulate this. And the challenge is made harder by the fact that we need energy for all these people. And energy takes water. All kinds of energy take water. And so I'm going to show you what's going on with energy. Texas is blessed with a lot of hydrocarbons. All the green are oil wells, all the red are gas wells. And all the new technologies have actually made us an exporter of energy. But you need water for this. And one of our big challenges is to understand how much water you actually need. And we'll get to that in just a minute. We also have an electrical grid. I should have put this slide earlier. Most of our electrical grid is not connected with the rest of the country. So we also have our own electrical. So we really are the right sort of place to try to put this all together to solve this kind of problem. And we have a lot of electrical. We have a lot of solar, because we have a lot of open land, and we have a lot of wind farms. In fact, we have more wind farms than at least anywhere else in North America. It's very impressive to drive by and to see. In fact, somewhere I had a picture that I couldn't find, which is the modern day Texas to me, where we have solar in the picture, there's a longhorn cow sitting there grazing, and there's an oil pump, and there are windmills, all in the same field. So we are shingling all of these things together, but what we want to understand is how does producing this energy, what does that mean in terms of land use and water? We know they're interdependent, and we want to understand that better, and we want to get to the point where we can say this is how they're interdependent, and this is what it means both for the water and for the land use. So let's talk just briefly about water first. So the interesting thing, right away I showed you that slide that said that Texas is stressed and we don't have enough water. Well, it turns out that the amount of water that goes into, this is in West Texas, and this is a big producing area right now. The amount of water, again, this is 10 to the 10 cubic meters. So this is, again, a huge amount of water, but the amount that goes into actually producing, to injecting to recover the hydrocarbon is not so great. Our big problem, there are a lot of blobs here, but the big two are down here. More water comes out of the ground than we put into the ground. And you have to do something with that water. That water is considered a hazard. And these are really big numbers. Now, fortunately, a lot of that water gets immediately re-injected to get enhanced recovery. So that solves part of the problem. But we still have something like 14 times 10 to the 10 cubic meters of water per year that we have to do something with. So as much of our problem is not, do we have enough water for us to drink, but it's what do we do with all of this hazardous water? And this is something that we're now realizing we have to invest a lot more time in. Right now we just have ponds, and that are not supposed to leak, and we have to do a better job on that. And those ponds take up space, and this gets into the land use part of the issue. We have to, when thinking about energy, not only do we have to think about water, but we have to think about land use. Fortunately, with satellite imagery, we can go in and at 1 meter accuracy figure out what the footprint of all energy is. And I'm going to show you just one example of this in West Texas. So here's just the land use map. This is again in the Permian Basin area. This is an area of very active energy production of all kinds. So this is just land cover right now. So this is just showing, you can see a lot of this is shrubland. It's not really used for much of anything. So let's first just put on the solar. Boy, you can hardly see that, at least I can't. So there are a whole bunch of solar areas in here, but their footprints aren't too big. Let's add in the wind turbines and power lines, and that's impressive. All of this green is the footprint of wind turbines. They have totally changed our landscape. They are a big ecologic player here, but not as big as when we start to now put in the oil and gas wells. You can see that gets really big really quickly, and this number is supposed to keep doubling as the years go on. So we're taking an area, when they were filming No Country for Old Men, they went to find the most remote place in North America, and it isn't in California or anywhere else. It's out here near Marfa, Texas. Well, it's not going to look very remote anymore with what we're doing. And then finally, if we add on all the power lines, look at all those red things, we've totally bisected our area. So we've changed the ecology, and it's really to the point that the impacts are substantial for all sources of energy. So while we agree that it's likely that the path forward is to diversify, having solar and wind and hydrocarbons and hydro are all things. We even have some nuclear in the state of Texas. That is good, but how do we figure out this fragmentation of our landscape, and what are we going to do about that? So that's really where we are right now, and how do we take advantage of these connections? Now that I've shown you, it's not easy to actually quantify what those things are. I'm showing you how we're starting to do that. Now we're working with city planners and ecologists to understand what these footprints of water use and land management are, to really start to prepare for this 50 million people that are coming down the path. And that brings us to, I think I'll stop here because I see the time, and it's definitely time to wrap up. But we're going from, I talked mostly about the environment. We're going past the environment now. We're working with bringing in, because the university realizes how important this is, our first grand challenge project at the university scale is to not only bring in the environmental science, but to bring in the health science, to bring in the urban planning, to bring in the policymakers. And so we now have 120 scientists in this grand challenge project from every single college at the University of Texas who are trying to work together to make sure that we're a resilient place and that we're around in another 100 years. So I'll stop there given the time, but I'm happy to take any questions, and I really want to thank you for your attention. Thanks a lot. You're speechless. Nice. Or they're cookies. Yeah. Yes?
So just after you do all of this research, so how do you convey this to decision makers actually? And how to, for instance, you have some policymakers in the research group. So how easy is it to make it, you told people that water availability is decreasing, and how to reinforce this in order to create an action plan or policies?
So this is a great question. The question is, after you've done this work, then how do you actually ensure that your new understanding is actually used and enacted in a policy way? And so I'm going to give you two little stories on this, because I think this is really important. And I've had a certain amount of experience in this. First is, if I talk with my people in policy, they'll say that science doesn't matter. So I have colleagues that will say, doesn't matter. It's all driven by something else. Now, that's not true. So what are we doing? First of all, we're actually bringing legislators in to look at this and to be involved in this from day one. But my personal experience, so I work a lot on coastlines and work on like land loss in the Mississippi River Delta. And I spent a decade with my colleagues trying to convince politicians how to affect change, how to break the levees of the Mississippi that have been there for 100+ years, to bring sediment back into the marshes that are disappearing at alarming rates. That has been only marginally successful. But here is what does work. And so I've taken a survey of my other colleagues who want to be not advocates saying, not activists, but advocates for the science to say, get it out there. We have gone to insurance companies and reinsurance companies and utility companies and given them this information. And it turns out that utility companies and insurance companies care deeply about these things. And they are in a position to affect change. If an insurance company or a reinsurance company tells the state of Louisiana, we're not going to insure your cities unless you have manageable plans, that carries much more weight than me marching up from the University of Texas and giving a PowerPoint presentation. And the same way, if the electric companies or the sewage companies, telephone companies, they know they have to be pragmatic. They have to solve these things because they know they're working within this changing environment. So I've gone from being worried that maybe it won't matter to realizing that we need to be more clever and talk with the pragmatists in society, which are those that have to deliver goods, not necessarily, at least in the US, I can only talk for the US, our politicians are not necessarily the most pragmatic. And so I'm going to put my emphasis there. Yeah. Yes, sir?
Texas may not be a model for a typical city for management of water and based on that management of land, space, and because of the high rate of production of hydrocarbons. So how would you plan for another city? What's the conclusion for a typical city, not for Texas?
So what's interesting about Texas is that we go from, in East Texas, from a place like Houston that has a groundwater table that's basically at the surface. And so they have too much water, to places like San Antonio, Texas, which is, I still think, the 10th largest city in the US. And it is by far the largest city that gets all of its water from groundwater. So we have everything from reservoirs to groundwater type systems to El Paso, which is the largest city in the US that is building desalination plants because all their potable fresh water is essentially gone. So they're building. There's a lot of groundwater, but it's very saline, so they're having to do that. So our way forward is not to say that there's just a typical city. It's to realize that there are many extremes here, and all of them are being folded into this. Yeah. Yes?
Developing the model to make the balance, water, energy, land. Major efforts. Collaborative work with foresters, with oceanographers, ecology, geology, you name it, landscapers, in developing that model. My question is, how reliable such a model, particularly in a state like Texas, in which you have that humongous, unpredictable hurricanes that could come in and dump in huge amount of water, as you mentioned, 1.1 meter in a couple of days. Would put the model upside down completely? How would you, even if you look at data for like 20 or 30 years, how reliable would these models be? And also, do you develop a model, various models for the state, for the areas that have extreme dry areas versus very wet, as you have indicated. So you have basically two major challenges there.
So two major challenges in model building. One is these extreme event. How do you ever build, but more importantly, validate a model where you have such extremes and yet you only have a few decades of really reliable data? That comes from, well, you have to have a model that can treat the extreme events, the heavy tails of distributions pretty accurately. And so it also means that you have to work with statisticians to decide how you're going to assess whether your model is giving you a very accurate result when you're looking at the extremes. I don't know yet whether these coupled models are giving us those results. The other question was, does one model fit all? If you're living in a location where some people have too much water and other people don't have enough, can the same model describe both of them? And the hope is that modules of that model can describe both of them. But honestly, what I've shown there with that coupled idea is we have pieces of that. Like we have the stream flow, the national stream flow model that with surprising accuracy predicts the whole network, the arterial network of the 48 states of the United States, the stream flow everywhere and nearly 3 million reaches. So parts of it work, but bringing in the groundwater accurately, the issues about my question is what's going to control land use decisions? I mean, some of it's economics, but a lot of it isn't. A lot of it is when the density gets that big, it's people are living there and say, now wait a minute, we don't want another 50 windmills in our backyard. They're actually surprisingly noisy. They're a little terrifying. They're so big. And that's a non-economic thing. And how are we going to bring emotional decisions into an economic model? Those are challenges, but it's where we're going. That's all I can tell you. Yeah. Yes, sir?
I've been working in water and now with water and policy for a while in Oklahoma, basically.
Okay.
So the thing is, the driver that I found out that we really need to look for the driver that moves your work, your science, basically. And it's not science for science. A lot of the times it should be the policy setting the driver, not bringing in people at the beginning. They should be driving it first, not us scientists bringing in the policy people. Because look at Houston and the growth of Houston. Most of the damage was done because the swampland was drained or paved over, and you got all that. So the scale issue at which you're working, you can start with the smaller communities and then work out at a grander scale. And that's where then you as a scientist can come in. And then the coupling of the model that you want to talk to, basically atmospheric versus ground versus subsurface, then that would come in and work at that scale and then expand to that.
Right. So so the comment is that we, as scientists, we can't just go in and say, hey, we're here to understand things and work forward. We need to have all of the stakeholders and those that are actually then leading to making the decisions on board from the very beginning. And part of the process, I think, is in a way what you're getting at there. And we agree. So part of this plan is actually a huge outreach to get people from cities and towns of all scale involved, get the information out there to get them engaged from day one. Now, how well that's going to work, we've started now for about 4 months, so I don't have any idea. But I do know that if we don't think big and if we don't try, we're not gonna learn something.
And David, I just wanted to add that one of our scientists actually predicted that incredible death-causing rain that we received for the lakes. And when she predicted this, like based on her models, there was a lot of doubt. I mean, no one, it wasn't publicized or anything, but her model was accurate.
Yeah.
So, science-based.
Our model is accurate.
Yeah. Yes?
I have a question about the methodology of the energy footprints you
Yeah.
have shown, because I didn't quite understand. Were you just footprinting the soil, like the area the infrastructure takes up, or were you also trying to footprint the resource depletion or water depletion of those energy sources?
So that's a great question. The question was, what was the methodology, the methodology of, it's late in the day, and I'm definitely jet lagged. So what's the methodology for looking at land use and when looking at the energy and the energy society water nexus? And it's confusing because I showed you two different things. One were maps of the footprint, and then the other was the blob diagram, which was actually inserted water, produced water, re-injected water, and wastewater. So to do this properly, you have to do both of those. And then what we haven't done as much of yet is there's been a tremendous segmentation of the ecology here. This was one of in the lower 48 states, an area where there was a relatively large amount of continuous landscape, and that is disappearing pretty quickly. So there's an ecologic challenge on our hands as well. Yeah.
Sorry, can I?
Yeah.
I actually, when I saw Earth in 2100, I thought you were going to talk about also phasing out fossil fuels.
Yeah. So yeah.
Is there like global warming to do with this? Is it part of the causes? I mean, sometimes you deal the problem at source by reducing the excessive use of hydrocarbons. I know there is definitely an attitude in the U.S. sometimes using big cars, using all the things. Is this part of the study, or is it to do with it?
Yeah, so the question is, the observation is, how can you talk about Earth in 21,000 and not talk about fossil fuels and fossil fuel production and use into the future? And you're right, it is part of it. And I didn't talk about it because, it induces a lot of passion in people, and I didn't want to misspeak because it's something that I have very definite opinions about, but I'm not a total expert about. But that said, clearly the role of hydrocarbon consumption in climate is a major part of this initiative. And one of the things that I never expected is, I mean, we drive big cars in the US, like you said, and we had a very large carbon footprint, and our carbon footprint has gone down a lot, not just because of the gas, I mean, not because of the gasoline in our cars, but we had a lot of power plants that used coal, and it wasn't the clean, they weren't particularly, they were coal burning power plants. With all of the relatively inexpensive gas that we've found in the US in these unconventional reservoirs, our carbon footprint has improved through a technology and a discovery that we had no way of predicting. So it's been a change for our better. I'm not saying that we have to figure out the energy issue. There's no doubt about that. And there are other things that are being done. Deep well, hydrothermal needs to be tapped more. We have deep basins where we should be thinking about hydrothermal in ways that we're just now starting to explore. But we have to do it. The point I wanted to just make is that if we're going to double in size in a state like Texas, and a lot of the whole world has high populations, we can't say that energy isn't part of our society, because we consume energy. It's one of the things we do really well. And so we have to do realistic and accurate bookkeeping of that to hopefully make the better decisions. Yeah. Whoops. Okay. Yeah.
In your model, do you include global warming has been driven mainly by human activity, or that nature is anyway doing from time to time a global warming event?
The climate models absolutely have greenhouse gases in them. So they have, yeah, and the greenhouse gases are, the change in that is human, is anthropogenic. So they have an anthropogenic signal in them.
But it's the main signal, the anthropogenic?
Oh, in the climate model, you know, there are a lot of things that, well, the greenhouse gases are a big part of the heating of the atmosphere. Now, that's not all of what the climate is. You know, if you just look at the energy stored on Earth's surface, the oceans, you know, water has a really high heat capacity. Getting the thermal structure of the oceans right is really important too. So there are a lot of parts that go in there. But in terms of the atmosphere, the greenhouse gases are in there in the appropriate way, I think. Yeah. Yes.
With the population growth trend you saw, it's increasing at exponential rate.
Yeah.
And this is in 50 years, and we're not sure that you can do a sustainable plan for it. What about like in 100 years or 200? Do you have like any start of plan to deal with it? Or
yeah, so that is a great, the question is, it looks a lot like, well, the observation was, it looks a lot like exponential growth. 50 years isn't going to get us very far. You know, what about 100 years and a few more out? Clearly, we have to be thinking about those things at the same time. The 50 years was chosen because, well, I'll leave you with one last thought. So I'm a scientist, and I like dimensionless numbers. And so a lot of you are engineers, so you like dimensionless numbers. You know, we usually use them to look at what terms in a conservation equation are most important. My favorite dimensionless number, though, has nothing to do with that. It's called the Garcia number, named after Marcelo Garcia, who's an engineer at the University of Illinois, Urbana-Champaign. And it is a dimensionless number that relates the time scale of the environmental response to the lifetime of a politician. And as long as that number is small, it's really easy to show them and to do the right thing. But when the environmental response is long relative to the lifespan of a professional lifespan of a politician, we have a lot of educating to do. So and we're talking about large Garcia numbers here. So we have to educate people. I mean, the other thing is to bring people in early. We have a huge outreach program at starting as early as we can. In the state of Texas, they can actually take earth science as an elective in high school, and just we have to get them in early so that everyone can help solve these problems, because you're right, we have a challenge.
One last question, and then I'll invite you to a reception.
You've had your hand up the most, I'm sorry.
In relation to what the US talks, I mean, there is strategies for efficient use of resources, I mean, water and energy.
Yeah.
Yes.
So the question is there a strategy for efficient use of resources? And the answer is that there are strategies for that, optimization ideas, but I've never seen any of them put into place. I mean, maybe I don't. Often, like in water, even within the state of Texas, part of who gets water when is when they first applied for water. So if 100 years ago they got a certain amount of water to grow rice in an area that's becoming drier and drier, that doesn't make any sense. But if they still have the right to that water, it's hard to plan optimization when we're using it in ways that don't make sense. So we are trying to adjust those things in our state, but we're far from taking advantage of optimization practices at a societal level. And the hope is, this is where bringing in the policymakers and the social scientists, and we have people in the humanities who are actually looking at the emotional response of people to events, because that's important, and we need to figure that into how we sustain ourselves. So.
If I may put an inflection on David's point, I think what he's referring to is really land use and legal structures. But in cities, for example, where you have possibilities for integrative design, where you can use different kinds of energy mixes, where you can reduce the amount of electricity you use by simply changing the way the building is designed, etc. That's something that's being pursued very actively. And I think there's a lot of hope there and a lot of room for young technologists, scientists, engineers to work on improving those things at the use level, at the end use level.
Yeah,
I'm sure he doesn't disagree with me.
No, I totally agree, and I'll just give you one example of that in Austin, where peak electrical is a problem because of heating, and I saw at one point the electricity went out today and some generators came on. We can
never happens.
we can get a lot of our electrical supplemented if we allow the city of Texas to control our thermostats. And so it's a good deal economically, but it means that everyone's house who does that may be a few degrees warmer during peak use hours than it would otherwise. So that's an example of very proactive optimization.
All right, let's give David a hand. I'd also like to just thank the Munib and Angela Musri Institute for Energy and Natural Resources for hosting and organizing this event today, and Dr. Hadar, Mr. Munib Musri as well for his support.
I'm very happy to have them. That's my
And
school also, University of Texas. I had the privilege and honor that I graduated from there in 1955.
please feel free to stick around, have a cup of coffee, and discuss what you heard today informally. Thank you very much, David.
Thank you.